So let's carry on a little bit. So as I said, I showed you a picture of a big diamond, which is not what you're going to use for these things. So these are pictures of the actual diamonds that you're going to use for them, and because they are really tiny, they're nanometer size. You need well, this is this is optical. This is an electron microscope picture, and this thing here is not quite such a. It's a little diamond, which is about 5 nanometers in diameter. And what you want to have is an NV center here, and then you just stick this to tip of a force microscope. So it's actually not so easy to make these small diamonds. So there are various strategies. Take a big one and grind them down, but then you don't get. It's hard to go to these 5 nanometer sizes. Then there's other strategies. Take explosives and mix a bit of coal or carbon or something like that in it, blow it up, and then afterwards you will find tiny nanometer-sized diamonds in the stuff that is left over afterwards. And the smallest ones you could actually find in meteorites, but this is a bit expensive to explain. And people sort of running around in Siberia trying to find little meteorites at the time now. So detonation diamonds is one possibility, but also this grinding down is getting better and better. But of course, then you also have this problem that not all the diamonds are the same size. Then you have to select them by size, and so there's all sorts of little problems that you still have. But the biggest problem actually is the surface, because it's not very regular. And if you take a detonation diamond, for example, then the outer layers are graphite and not diamond, and then inside is somehow the diamond. So you have to get rid of this graphite. So you use all sorts of acids, and once you have burned away the graphite, then you have to somehow treat the surface to make it regular. And so what people, for example, do is they take I keep forgetting the name in English. HF. That's sort of an awful acid that you use. That you I'm not sure for acid. There you go. So you can use that, and in the end you can cover the surface of the diamond actually with fluorine atoms, for example. And then it's a bit like Teflon, more or less. So it doesn't stick to very much anymore, and it's a very well-defined surface because it's all the same fluorine atoms. Problem there is that the fluorine atoms actually have a nuclear spin themselves, and therefore they will flip-flop around and they will create noise. And now what I want to show you is first, so one thing you can always do, you can do this decoupling, but you have to use very intense fields. And that causes problems in itself, and I show you what the problem is, and then a trick to get around this, which might be useful also for quantification. And then I show you how you can take this disadvantage of having all these fluorine atoms on the surface of the diamond with all their nuclear spins that are sort of flip-flopping around, that you can actually use this to build a quantum computer, at least in theory. So that's what I'm going to do. So here, so it's the same thing again. So I have this spin here, spin down, spin up, and I drive it with my, so this is electron spin, for example. I drive it with my nice microwave field. I create these stress states, and these stress states are sort of less sensitive to environmental fluctuations because of this argument that you need energy to go from here to here. Okay, so the better you want to be protected, the harder you drive the system. And that's fine. You can do this in principle. So you take your microwave source here, and so at low intensities it looks sort of, it appears to you like this. So I mean it's really nice constant field, no fluctuations on it. And you crank up the power, and then you will start to see that actually it's not quite constant field. Yeah, and you crank up more, and you see there are more fluctuations. And so when you do this, so you have now a field that you use to drive this spin transition here, and its intensity is fluctuating. Well, what does that mean? Well, the energy separation of these two spins, of these stress states here, is proportional to the square root of the intensity. If the intensity is fluctuating, then this energy difference here will fluctuate in time. So you get dephasing. So at some point it seems that if you drive harder, then yes, you're protecting better against sort of the noise from the environment, but actually you're introducing noise yourself, yeah, by the intensity fluctuations of your field. And so at least, I mean, the source that we had in Ulm had a relative intensity stability of or fluctuation of 10 to the minus 3, so 1 part in 1,000, which is actually, I mean, when you crank up the power, you get a lot of noise from this. And so this is really a problem because, well, for realizing all these things, you need a lot of power for the decoupling. So what could you do about that? So again, hardware approach, fork out a lot of money and buy a better microwave source. That's solution A. Solution B is think a little bit and use the same microwave source. So no extra expenditure in money, but still you get a much better protection against noise. So, well, from here to here, we drove this spin to protect it against dephasing noise. So we have this one. So now these ones are fluctuating and say it's tough for dephasing noise. Why don't we just take another microwave field that actually drives a transition between this spin and that spin? Okay. Well, if our argument from before was right, then this should now protect against any fluctuations in this stress state basis. So it should protect against the intensity fluctuations from the microwave source. So what does that mean? Well, actually that means, so we have two fields now. Right. One is the first decoupling field that is on resonance. And then we have another one which is actually detuned with respect to this resonant field by an amount which is exactly the Rabi frequency of this field. And that, in the dress state picture, will actually be equivalent to a field that drives transitions between those two dress states. So that's the idea. In practice, actually, you would like to have another field that is slightly red detuned, so has a frequency that is lower by the Rabi frequency as well. Then you have a pair, and then it's particularly symmetric. And so the claim would now be, well, this field, the red one here, protects against the environment fluctuations. This kind of pink, no, well, whatever color that is, protects against the fluctuations from the red field. And then you can iterate this if you like. If you're still not happy with the stability of that field, because this will of course get fluctuations from the intensity fluctuation of that field, well, you put in another one, and another one, and another one. And all these can be derived from the same microwave source, basically. It's only a small detuning, it's the same source. And so the question now, of course, is that sounds like a nice, cost-efficient way of getting better protection. And the question is, does it work? And so, well, you can prove it mathematically, of course, but in the end, you want to actually show an experiment. So that we tried actually in a real diamond, in the real MV center, and we showed that in this way you can get better protection against noise. So what do we see here? Well, here we basically have, here's time in microseconds, and here what you see is sort of the population of the dress state electron spin, so whether it's up or down. Okay, and so what you then sort of can measure is you can measure now, you check how long does the system remain coherent in the presence of the rest of the diamond. There's all sorts of dirt in there, some little nuclear spins that jiggle around your electron spin. And so what you do is you try to protect against these fluctuations by putting in a decoupling field which has a strength of 40 megahertz. So that's a Rabi frequency of 40 megahertz. And we chose that because we were sure that this is enough to really decouple from all the noise in the diamond. And the result of that measurement was that you get a coherence time of 2.5 microseconds. And this loss of coherence is entirely because of the fluctuations in this in the intensity fluctuations in this field. And so now we say, okay, so if our idea is right, now we switch on another field, much weaker. In fact, the intensity is a factor of 1,000 smaller than that of the first field. So on its own, it wouldn't do a thing. Yeah, you will not see anything. Now we switch that on. Okay, we switch that on, and then we get some results. So we have now two frequencies. So of course we see some beating between those two frequencies. And the question is really, how quickly does the amplitude of the beating signal goes down? And well, I mean, you can see that it goes down much, much more slowly. And this was actually the best value that we could find. And so when you choose different field intensities for the second order field, then you will see when you just have one field, then you get 2.5 microseconds. Then and here's a measurement where you have a field that is 40 dB smaller. Then you get already 7.5 microseconds, and you work your way up, and at about 30 dB smaller, so that's a factor of 1,000. You get 25 microseconds, so you gain the factor of 10. And then, of course, if you make this second field more and more intense, then its own fluctuations will start to cause a problem, and the decoherence, sort of coherence time goes down again. So instead of making this field more intense, what you would have to do is you would have to shine in the third field, and maybe a fourth field, and so on. And in this way, in principle, you can prolong the coherence time considerably. And so, well, I find that more convincing than a theoretical proof of it. I mean, it certainly works very well in a real diamond. Okay, and things like these. So, sometimes it is helpful to first think a little bit, find a nice little trick, instead of sort of trying to improve your hardware of your experiment, which in many cases might involve a lot more money and a lot more effort than just putting in another field. Right? So that's a nice little trick that you can use. Okay, so here are some examples to what you could in principle apply this to. Nothing of this has really happened, but it's really it's an interesting example. So this is actually an ion channel in the cell membrane. So when I move my arm, so then I send nerve pulses down my arm that makes my muscles contract and all these sort of things. And what happens there is that, of course, we build up potential differences, for example, between inside and outside of a cell or a neuron or so. And they have to be equilibrated at some point in a controlled fashion. And so that is done by using ion channels that transport ions into the cell or out of the cell. And so this is an extremely important process. So some of the most poisonous animals on the planet will actually attack the function of these ion channels. And if they stop working, well, then you can't move and you just die. And so also there are various diseases that are related to malfunction of ion channels. And so it's pretty important to try and understand how these ion channels actually work. And so one way at the moment to measure, for example, the ion current going through is that it's a so-called patch clamp technique. So you put a pipette or so around this here, and there's some liquid in there, and then you can actually try to measure the current that goes through this ion channel. And the current is small, but not extremely tiny. It's about 10 to the 8 ions that go through this per second. And so you can sort of measure that, but this is not an easy to do technique, and it's not done on the living cell, and so it's really tricky. I mean, the guys who invented that, Nea and another gentleman whose name I've forgotten, they got the Nobel Prize for this 25 years ago. So now, in principle, with an NV center, you can measure the current that goes through this ion channel by moving the NV center close, and then you have charges moving past, and moving charges create magnetic fields. In fact, in this case, passages at random times, so you have a little bit of random magnetic field, and so you see actually in the detector randomly fluctuating magnetic field. You can measure that, and in principle, you should be able to actually measure the current that goes through this ion channel. So that would be a neat sort of application where you don't have to put this sort of big pipette and stuff like that anymore, but you just move close to it and Right, so that would, well, magnetic fields are really small, but it should be in the just about doable. Then there are, well, catalytic centers in enzymes. There are magnetic fields being generated here. This is also a nice one. So you can have actually nerve pulse propagation. So you can actually follow the propagation of the nerve pulse through whatever synapse or so. And so you can make, in principle, all sorts of kind of measurements of, you know, processes that are happening in your body. You could even imagine that perhaps you can measure currents in the brain, and I mean magnetic fields that are generated there. Yeah, they're very small. It's a very sensitive detector. And right, well, nothing of that, as I said, has really happened, but it's all sort of nice possibilities that you might be able to do with study with such detector. And well, to make this work, you need quantum optics, quantum information tricks, a bit of solid-state physics, and so everything comes together to make these things work. Okay, right. So that's so much for the sensor part. And now, okay. Well, that's more an advertisement that this is the best sensor possible. Better than anything else, if it works at all. So, I mean, okay, so let's say if you want to determine structure, that's right, I didn't really say that. So how would we determine the structure of the protein? So we take the protein, and the protein, of course, contains, for example, hydrogen and various other atoms that have nuclear spins. So these nuclear spins, we can determine their positions. And in fact, we can either do directly, we measure here's a hydrogen, there's a C13 or so, here's a phosphorus, and then we just map out where they are. Or we can actually use the fact that when these spins are very close together, then they're interacting quite strongly with each other, so they get a shift, and then you actually measure this energy shift. And then you can measure the pairwise distances between the spins that you have in your protein. And if you have all these pairwise distances, then you can reconstruct the structure from it. Okay? And so that's also the way NMR would do that. X-ray diffraction is a different way, but there you have the problem that you have zero temporal resolution. You crystallize the stuff and it's fixed, and then you determine the structure. But you have a fantastic spatial resolution, whatever, 1 angstrom, so almost atomic size resolution. And the problem is that it's not done in with the real protein. So the problem is, you take the protein, many of them can't be crystallized. Even if you manage, you don't know what you do to the protein in the process. You have no idea whether this is really the thing that is acting in your body. So you want to have a process that has the same resolution in space and otherwise the same abilities, but you don't need to crystallize. And that's what this detector might actually be able to do in many ways. Okay, so now let's come to quantum simulators. Right? So, well, okay, this is a bunch of possible implementations. So, I mean, of course, here we see a picture of an ion trap that I stole from the Innsbruck website. So ion traps are a wonderful candidate for quantum simulators. And then there's ultra-cold atoms. So you make Bose-Einstein condensation, you trap the atoms in an optical lattice, and then you get really a lattice system, and you can make all sorts of wonderful physics in there. I mean, now people are really starting to make proposals how you could actually probe quantum electrodynamics, for example, and lattice gauge theories, and all sorts of stuff like that. I mean, so there's really a lot of potential, but of course, this is a system that is also not so easy to handle because you have to create a PEC, you have to trap it, not so easy to get single site resolution, although even that is now possible. And I mean, it's a lot of technological overhead that you have to invest to realize this. Okay, so it's really, I mean, it's really hard to do, I would say. And certainly, I mean, if you drop this experiment to the floor, I mean, it's broken. And so the advantage, of course, of what I want to tell you now is something that you can drop it and it still will work afterwards. Well, it's a bit exaggerated, but it's very nearly like that. Here's superconducting qubits. So this, I mean, so this is more like nanokelvin or so, microkelvin, millikelvin. So all pretty cold as well. Yeah, so ideally you would like to have something that is room temperature. So like optics, for example, optics works at room temperature. Optics is not so easy to scale because, you know, making photons interact with each other is not a completely trivial thing. And so this has its own challenges. In NMR, this also works at room temperature, except that it's not a quantum computation because the state is really never really entangled, at least not in the standard liquid state NMR simulations, and so it's not completely clear whether you can really make a quantum simulator. And so what rides to our, well, rescue perhaps is again the diamond. And now we take exactly this problem that I mentioned, namely we cover the surface with nuclear spins, with fluorine atoms, and we turn this, and this caused the problem that the nuclear spins interact with your detector and they make noise and you have to protect against this. So now I want to turn this on its head and use this as a great strength. Okay? And all the things that I've explained to you, all this decoupling and how to sense spins and so on, all this will now be used to actually build a quantum simulator. Or at least to write down a theoretical proposal of how to build a quantum simulator. And so the way to start with this is, well, as I said, you take a diamond. Actually, you don't take a nano diamond, you would take a nicely sort of CVD diamond, so chemically vapor deposited diamond, so it's very nice flat surface. And what you do is, you first put some NV centers close to the surface that you can do. And I told you at the very beginning of the talk how you might be able to do that. And then you fluorinate the surface, so you use all sorts of, you take this HF acid, and in the end, you get actually a surface, diamond surface, where each carbon atom binds exactly to one fluoride. And now the diamond has different surfaces depending on the cuts that you're making. And so one surface is the so-called 1-1-1 surface, and it gives rise to a triangular lattice in the end. When you look from the top, you will see that the fluorine atoms will arrange in a triangular lattice. So that's one possibility. If you take a different cut here, that's the 1-0-0 cut, then in the end, what you will get is actually a square lattice. And so it's a bunch of fluorine spins sitting on a regular lattice in this almost a perfect lattice because the diamond lattice is nearly perfect. The distance is 2.5 angstrom. That means actually that these two nuclear spins, they will be interacting with each other and exchange, for example, energy at a rate of about 6.8 kilohertz. Which is actually, well, on the one hand you could say sounds like a rather small number, but when you compare it to the coherence times that you can achieve with nuclear spins, then this is a very, very large number. So there were recently experiments that demonstrated coherence times which were of the order of seconds. Okay? So you can actually get very long-lived coherence, while at the same time you can exchange, make interactions that are at a very high rate. So these are two possibilities. And then another way that you immediately think of when you start to wonder about these things, of course you can use graphene. This is really very fashionable material at the moment, so it's a single sheet of carbon. And initially we had thought of the following. We just thought, okay, let's make graphene that is made out of carbon-13. Carbon-13 has a spin, nuclear spin, and so we would have this nice hexagonal lattice of carbon-13 spins. And then we thought, well, okay, we will manipulate it with our NV center, and we have a wonderful quantum simulator. Until we remembered one thing, namely graphene has no band gap, so it absorbs a lot of light. And so actually when you have an NV center underneath a sheet of graphene, you're not going to see it. And you cannot manipulate it with light, and therefore you would have a real problem. Then we fortunately discovered that Novoselov and Geim, so the guys that made graphene a few years ago, they actually created fluorographene. And so it's graphene, and it has on top a layer of fluorine, and on the bottom, underneath a layer of fluorine. and it has a huge band gap of 3.8 electron volt. And so you can actually now put this and lay it on the surface of your diamond, and you have a nice hexagonal lattice of spins. So you can see that you can make a lot of different kinds of lattices here. And nowadays, okay, so this is all carbon. So I just come from a summer school where Novoselav was explaining stuff, and now they can make all sorts of one-dimensional materials, boron nitride, for example, and they can stack them on top of each other and all sorts of things like that. So there's a whole possibility here. So you can think of properties that you would like to have, or lattice structures that you would like to have, and you might be able to do that in this way. And again, the nice thing is there's no optical lattice that you need here to hold these nuclear spins in place. Yeah? They're just sitting there, and actually, so this they call, I mean, Novoselav and Gein, they call this sort of, it's basically like Teflon. So it's really, it doesn't react very much with other stuff because the fluorine really binds very tightly to the carbon. So it's really sitting there, and I mean, you really have to make it very hot to break off the fluorines again. So this is sort of a nice way, and that's why I say, so if you want this, I wouldn't drop on the floor because this sticks and you can put it off again. But let's say if you make a diamond or so with such a surface, in principle, you can, I mean, you could drop it or so, I mean, the fluorine will probably just stay where it is, and it will be unaffected. Yeah. Of course, I'm lying a little bit because you don't want to have the surface dirty. So if you touch this, I mean, you will put all sorts of dirt on it, and this dirt contains electron spins and nuclear spins and all sorts of stuff. And of course, it will be very close to your surface, and therefore it will cause problems. So in reality, you will not drop this diamond anyway. But it just sort of, you know, in principle, this is, if you store it at room temperature, this will last for a very, very long time. So that would be sort of the design. But now, of course, you have to solve some problems, because actually, just like this doesn't help you at all. So here we have this layer of these nuclear spins, and here we have this NV center sitting 2 or 3 nanometers underneath, and that will be the tool with which we can manipulate the surface, because we need to do a few things now. Nuclear spins at room temperature, even at 1 Kelvin or liquid helium or whatever temperature, they will point up, spin up and spin down will be almost 50-50 distributed. So this is a completely mixed state, just like in liquid state NMR. This behaves classically in pretty much every respect that you can think. So this is not useful. So what you have to do is, you have to actually polarize these nuclear spins first. So in the end, what you want to achieve is that all of these nuclear spins are pointing downwards or upwards, but I mean in a one defined direction that you choose. So it has to be a low entropy state. So it should be almost pure, and that is always the starting point for any quantum simulator that you want to sort of build. You have to have a very pure initial state. So how would you do that? Well, now you just have to remember what I was telling you before, so I hope it's there. Yeah. One thing is, we can, I mean, this NV center, as I explained to you, it can sense a nuclear spin. It can sense the presence of a nuclear spin. Well, how did we do this? Well, we first polarized the electron spin of the NV center, which you can do relatively easily with light. And then we saw an energy exchange between the nuclear spin in the environment and the electron spin of the NV center. So they were doing this. Right. So that's exactly what we want, no? If the spin of the nuclear spin is pointing up, then afterwards it will be pointing down. If we prepare the electron spin down and the nuclear spin is already down, then nothing happens. So after this procedure, we will have reduced the probability of the nuclear spin of being pointing up to, we have reduced that probability, so on the net effect is the nuclear spin will have a higher probability of pointing downwards. We repeat this procedure many times, and then we slowly get rid of the randomness in the nuclear spin array. And so this is how it would look like. So you would have here, this is your bunch of nuclear spins. This is your NV center, and now we prepare the electron spin and spin down. We have the, for example, one of these nuclear spins. This one, for example, up. Well, goes down, and this one is shifted. And then we do that again. Well, the next one flips, flip, and one after the other, we actually polarize these nuclear spins. And it's exactly the same procedure that you use for sensing. We demonstrate one, we have the other. So, of course, you have to, I mean, this is again sort of theory talk, and then you have to not do an experiment, but you have to do a numerical experiment actually. So we took a lattice of spins, we prepared them, we put in all the Hamiltonians, all the noise and all these things, and then you actually see that initially you have a 50-50 probability for the spins pointing down and pointing up, and then this probability for spin down increases and increases, and after a few milliseconds you actually arrive at a 98% polarized diamond, in theory. In practice, we are currently trying to build this. And well, I always say this very loosely, so we do a bit of theory, and the Fyodor Yeletsko's group is building actually these things really and does experiments. Now, actually, what I just told you is not really true, because nobody complained, but there's a little problem that I didn't mention. As I said at the beginning, these nuclear spins are actually interacting with each other. So you do not have individual spins that you would sense. One is sitting here, you measure it, or you put the spin down. You actually have the eigenstates of the system. Yeah? So it's an interacting many-body system. It has many different eigenstates, many different frequencies, and it would actually be very hard to do this protocol directly on these eigenstates, because we don't really know what the frequencies are, and they are quite closely spaced, and it's very hard to do this. So what we actually have to do is, first, we have to decouple all these nuclear spins from each other. Because if they are not interacting with each other, then otherwise they are identical. So you have then a set of individual, independent, identical nuclear spins, and then you can use this protocol. Yeah. And so we have to use these decoupling techniques that I have shown you before. So what you do is you shine in radio wave frequency, radio frequency radiation. That will actually rotate these nuclear spins, and so their interaction with each other averages out, and so they will behave like individual, independent nuclear spins. And only then you can actually make this protocol. And so this uses these ideas from decoupling to prepare also this set of nuclear spins. And okay, yeah, I forgot to switch that. Right, and then, well, then you have put everything together basically. There's one thing missing still. Of course, in the end, we have a quantum many-body system here, and then all sorts of condensed matter people will come and calculate all sorts of wonderful phase diagrams of this little magnetic material that you have made. It's a little magnet. I mean, lots of little magnets that are interacting with each other. It's nuclear spins. Each of them is a little magnet. They're interacting with each other. It's an artificial magnet in 2D. And so there are all sorts of phase diagrams that you can make. You can study phase transitions. And so this is, well, condensed matter people find this very exciting. But in the end, you actually have to show that you had a phase transition, for example. So one phase transition that you know is when you have a magnet, a real magnet, so it has a spontaneous magnetization, then you warm it up, and at some point it loses its magnetization. Okay, so that's actually a phase transition, and so you would like to, for example, be able to study these kind of phase transitions or equivalents at zero temperature. So you have to be able to measure the magnetization of your nuclear spins. Well, okay, but I've just shown you how to do that, because I can even measure the state of an individual nuclear spin, and so therefore I can also measure the total magnetic field that this whole ensemble, this whole layer of nuclear spins is creating at the point of your NV center. With the global magnetic field, you measure that magnetic field, and you therefore know whether all these nuclear spins are pointing up or down, or whether they are randomly oriented. Okay? And so again, so all this sensing stuff that I explained to you at the beginning will be absolutely essential for building something like that. And right. So that's sort of, I mean, without any formulas and any proofs. So this is how you can see how you can actually build a quantum simulator using tiny nuclear spins that you stick on a piece of diamond. And that's what I wanted to tell you about diamonds. As I said, tomorrow something else. Tomorrow it will be more like quantum biology. Okay, thanks.
We have a bit of time before we should be heading off to the coffee and post session, so if there are any questions.
So you've got one NV center overlooking a bunch of fluorines, right?
Yes.
So how do you address them individually? I mean, do you have to assume that they all have very different thermodynamic ratios? Because how do you make sure that you don't talk to two of them at the same time?
Oh, it's okay that I talk to two of them. I mean, if you mean for the polarization?
Yeah.
Well, I mean, I may talk to two of them, and then, I mean, one of them, I mean, so they both have the chance to do a flip-flop with my electron spin, but because the electron spin can only go down from spin, down to spin up, it will just extract one excitation either from this one or from that one. I don't care.
If it talks to two, you could have dark states as well, right? If you, for example,
that's true.
Yeah.
And so to overcome that, the simplest way is actually to put a little bit of magnetic noise. And so you put a fluctuating gradient field or so, for example, and that kills off all these dark states. And in fact, that is something that, we had to estimate basically what do we need to get a reasonable cooling time. But so in principle, these things you can do.
Martin, yeah, I had a question about your continuous driving. So just check my understanding, that's what NMR people call spin locking.
Yes.
So I think you made a point that it's better than having these pulsed high voltages, because you could get away with a lower power. Yeah, continuous driving. So, and the continuous driving is some frequency only, and so that will work nicely, provided only there is a higher frequency than the environmental noise signals. If I use that same frequency omega, or for instance, to do discrete pi pulses, doesn't that mean then that the frequency width of those pi pulses is broader than the amount the original levels were jiggling around by? And therefore for the same power level, I'm claiming it just
no, but if you do these pulse things,
yeah.
then actually I'm not sure that I mean, so the relevant quantity for the pulse schemes is the separation between individual pulses. Yeah? So they have to be more rapid than the memory time of the environment, or as a frequency, they have to be higher frequency than the bandwidth of the environment. So, but if you really want to have individual pulses, then these pulses have to be much shorter than the spacing. And so you need a higher Rabi frequency than you would need in the continuous. So of course, I mean, in the end, I mean, it sort of naturally evolves into this, well, everything becomes continuous. But if you want to have these pulse schemes, and this is how often people are doing with CPMG or so, you use too much, you use a higher frequency, Rabi frequency than you would strictly. And I mean, so I say we proved this, I mean, we proved that the continuous scheme is a local optimum.
And the other question on the same thing was when you have, you then go to the contraction into the scheme, and you had a sideband, you drove one sideband in the microwave frequency. So, you know, we had a go through this as well, and we actually had two sidebands, just because it was easier to.
Yes, it's also better.
It is actually better to.
Yes, it's a factor of 2 better.
a different phase relationship?
Oh, I think yes. I'm not sure. I think yes. But that shouldn't be a problem. They're around the same source. So, I mean, in the original paper we said, well, one sideband, but actually then jumping sort of on the against.
So this process of aligning all of the fluorine spins is kind of like cooling the temperature of those spins. So what is the temperature and how does it compare with?
Well, okay, boy, the temperature would be, if you would express it in temperature, but it depends on the external magnetic field, but I mean it would be, boy. I like to express it in probability of pointing downwards, so 95%. So, it really depends on the applied magnetic field as well, but I think this would probably correspond to nanokelvin or something. Yeah.
I just wonder if it's the coldest is in a BCs or something like that.
Doesn't call it motion, does it?
Oh no, I just mean the
spin temperature.
The spin temperature, yeah.
I don't know whether it would be cold or not, but I mean, really the relevant point is not actually what is the temperature, but what is the entropy of the system. That's what you really want to know. I mean, yes.
So in the last slide you showed you had these phase transitions and stuff. Is that, and you had J2 and J1, are these couplings you can really control quite accurately?
Yes. Really. Yeah. So, I mean, so of course this goes into nitty-gritty detail and so on, so you have to apply the right kind of radio frequency fields to those spins, and then you can actually adjust the couplings between neighboring spins, but not individual, but I mean you can sort of say, well, all the spins that are sort of separated in this direction, they will have a certain coupling rate, and the ones in the triangular lattice that in this direction is a different one, for example. That sort of stuff you can do, but it's all more or less translation invariant, because you can imagine radio frequency waves have an enormous wavelength, and here we are talking about maybe 10 by 10 nuclear spins, so it's 2.5 by 2.5 nanometers. So, but in principle, you can control this, and so you can create frustration, for example, where you teach the lattice or the spins to try and align in an opposite way. And if you're in a triangular lattice, then you can see that, well, they all try to be anti-parallel, and they can't. And so that's called frustration, and this has, well, interesting consequences in these many-body systems. But that's a lot of, really, this is terrible. I mean, when you go through these calculations of how to make the coupling and so on, this is really painful. Yeah. There was someone else.
I have a question. For the concatenated noise protection, is that an NMR technique as well, or do you elsewhere?
I would actually imagine that someone in NMR was so clever to figure that out, but we don't know. So, okay. But I mean, these people had 50 years time, and they are really rather clever. So I would imagine. But it might be that it was not necessary for them. That's also.
If spin locking was not important for them, then they might have no need for it.
So I mean, so far nobody has told us that, oh look, 37 years ago this and that person has done that. So it might be new, it might not be new, but to be honest, it's still nice to figure it out somehow.
Are there more
You had one? No?
questions? If not, let's thank Martin again.